Good afternoon, my YouTube viewers. It's Crystal here. I'm just here because I wanted to do another code review. And what I'm going to do a code review on is the mtcars dataset. And I'm going to endeavor to perform a simple linear regression. And I'm going to use it, it's going to perform it in Python with several libraries. So you can pick out the library that you like the best. So the first thing that I did was I got the mtcars dataset, and I got it off of a GitHub account. And what else did I do? So I got the mtcars dataset. I wrote the program in Google Colab, which is a free online Jupyter notebook hosted by Google. And the only thing that I can say about Google Colab that's negative or critical is the fact that it does not have an adequate undo function. And because it does not have an adequate undo function, you need to be very careful not to accidentally overwrite or delete variable code. And I've done that in the past. So you need to be really careful about that. If you do accidentally overwrite or delete variable code, you might be able to go into the save history and retrieve it. So I've done that in the past too. But it's not always possible to do that, so you still need to be mindful. So after we've created our Jupyter notebook, first thing we're going to do is we're going to load our data set. We're going to import pandas as PG. The reason why is because pandas creates data frames and it processes data. And we're going to read the data set from the GitHub account and turn it into a data frame. So this particular data set only has 32 rows of data, and because it only has 32 rows of data, I decided not to split it because this is just for academic purposes, and since it's such a small data set, I decided the best thing to do was not split it into training and validation sets because we just want to see the root mean squared error, see how well it performs. And after we have downloaded the data set, then what we want to do is we want to define our x and our y variables. Your y variable is your target, and it's going to be mpg, 4 miles per gallon, and your x variable is going to be DISP, and I'm not sure exactly what DISP stands for, but it's DISP. You're going to take x and you're going to convert it to a data frame. And so your x variable is 32 rows by 1 column, and your y variable is a series of 32 rows. And then what we're going to do is we're going to normalize, standardize or normalize it. We're going to normalize x, and then so I wasn't sure exactly what to do because sometimes you standardize it, sometimes you normalize it, but in this particular instance we decided to normalize it. So max x equals np.max x, and x equals x max x. And so what that does is that reduces the data set to a scale of 0 to 1. And we've also imported our NumPy library. And what your NumPy library does is it creates NumPy arrays, and it also performs mathematical computations on the data. Now we're going to use Seaborn, which we've imported, to create a scatter plot of MPG and DISP, but I think I got that wrong. I think it should be, I think X is DISP and Y is your MPG. PG. That's one reason why I like doing these. Code reviews, because the code reviews, like if I've made a mistake, then the code review helps me to correct my error, which is what I've done on this occasion. Now we're going to use, after we've done that, this is going to be simple linear regression, which means you've got one column of data for the x variable or the independent variable, and one column of data for the y variable or the dependent variable. And we're going to use sklearn's linear regression. So we're going to import sklearn's linear regression into the program. So linreg equals linear regression dot fit xy, ypred equals linpred dot predict x, and then you've got your ypred. And then after we've got the ypred, then what we're going to do is we're going to calculate what the RMSE is. And so we calculate the MSE, and after we've calculated the MSE, we get the square root of the RMSE, and that gives us a 3.14 or 3.148, which is very good, which is a very good reading. And if you want to look at the actual values against the predicted values, you can always look at the actual values against the predicted values and see what happens to it. And then another thing is you can import matplotlib.pyplot as PLT into the program, and you can plot the predicted values against the actual values, and you can see what it looks like. So it's always a good idea to visualize it, because when you visualize it, you can see what's actually going on. And now what we're going to do is, after we use sklearn's linear regression, we're going to use statsmodels linear regression. Statsmodels is a statistical library. So we're going to import statsmodels into the program. So model equals sm.ols. OLS is ordinary least squares, which is what they call linear regression, and it's going to be y and x. Results equals model.fit, and print result summary. So you get a statistical summary. You get a statistical summary of this simple linear regression. So then what we're going to do is we're going to predict on the x variable, ypred equals results.predict x, ypred equals ypred.ravel, and then ypred, and then so you can see this is everything that is ypred. And we check our RMSE, and it's 14. So the RMSE is not as good as the RMSE in sklearn. Okay, and then what we do is we plot the predicted values against the actual values, and you can see that it doesn't look as good. And now what we're going to do is we're going to use JAX linear regression. And so we're going to import JAX into the program. So y equals jmp.asArray y, x equals jmp.asArray x, and then we're going to use we're going to normalize it. Max x equals jmp.max x, x equals x over max x. So we're normalizing it. So def normal equation, beta equals jmp.dot, that's your dot product, in brackets jmp.linear alg.inverse, that's linear algebra and it's inverted, jmp.dot x transform comma x, and then jmp.dot x transform over y, and then you've got your predict, and that's going to return beta. And then you got your predict x beta, return jmp.dot x beta. So now you've got beta equals normal equation x, y, and predictions equals predict x beta, and then we're going to flatten the predictions, and you get an RMSC of 14.88891. Let's see what our other RMSC was. So that's the same as stats models. Okay, and then we're going to compare the actual values against the predicted values so you can see what they look like. And then we're going to put it on a graph to visualize the actual values against the predicted values. And so you can see that looks like the stats models one. And now we're going to use NumPy linear regression. So we're going to import NumPy and into the program, which has already been imported, and matplotlib.pyplot as PLT has already been imported too. Y equals np.asArray y, x equals np.asArray x, and we're going to normalize it. So all the values are going to be from 0 to 1. And then we're going to define the normal equation, which is the same as the JAX equation, except you're using NumPy and not JAX. And then we're going to define the predict equation, which is the same as the JAX equation, except you're using NumPy and not JAX. So beta equals normal equation x, y, predictions equals x comma beta, and then you flatten the predictions, and then you get your RMSC, which is 14.8188891. And then you can take your values, you compare the actual values against the predicted values, and you can see what they look like. And then now we have made a graph, and we plotted the graph so you can compare the actual values against the predicted values, and you can see that that looks the same as JAX and it looks the same as stats models. And so you get the same value with stats models, JAX, and NumPy, but sklearn gives you a better RMSC. It gives you better visualization. But I don't have the code for sklearn. I wish I did. I wish I could get the sklearn code, and then maybe I could try that and experiment with that some. And now what we're going to do is those linear regression models that I used, they were just standard linear regression models. And I tried a Kaggle simple linear regression, and I tried to get that to work on the mtcars dataset, and I couldn't get it to work on the mtcars dataset. But I decided to go ahead and give you the code for simple linear regression just so you can see what it looks like. And so that's not going to be y. So you're going to import NumPy, Seaborn, and Matplotlib. You're going to set your random seed as 1. I'm going to make that 42 because the guy who wrote Hitchhiker's Guide to the Universe said the answer to everything is 42. So I thought, well, just to keep everything standardized, I'll just make everything 42. So you're going to make a set of random numbers, set of 1,000 random numbers. That's going to be your X. W is going to be your weights. It's going to be np.random.randn. And bias is going to be np.random.randn. And then y equals x times weights plus bias plus the random number times 0.09, and this last term of np.random.randn is to add noise. And then what we're going to do is we're going to plot on a graph what it is. And you can see that looks like a very nice plotting. And then we've got our simple linear regression, which allows you to input one column of data. So, and this is a class as well. So def in itself, self parameters is a dictionary, and self.m equals none. You set up your predict, and self.m equals x shape 0. It says try ypred equals self.parameters w1 times x plus self.parameters b. So that's your weights and bias plus bias. Return ypred, except print first fit your data, then predict the values. Now we're going to check the cost, and accepts ypred and true, y true. So that's going to be, I think, like your error. Return np.sum, np square, ypred minus y true over 2 self m. And then now we're going to fit the data, and they give you some more code to fit the data. And then after you fit the data, then what you're going to do is you're going to make a graph of that. So here we go. Model equals simple linear regression. Model.fit xy. So it gives you 1,000 iterations. And you can see that the more iterations, the lower the cost, or the lower the error. So ypred equals model.predict x, and ypred is flattened. So here's your ypred, and then here's your cost. The cost is 0.0042, and we create a diagram of that, of simple linear regression, and you can see that the simple linear regression, the actual values fit nicely across the regression line. And we check our RMSE, and RMSE is 0.09. So I tried to use the simple linear regression on the mtcars dataset, and I couldn't get it to work. And even though I couldn't get it to work, I thought, well, I'll go ahead and use simple linear regression, show you what it looks like, and you can try it yourself. You can give it a go and see what happens. So I'm going to go ahead and conclude this video because I've covered sklearn, stats models, NumPy, and JAX. So I've covered 4 libraries where you can compute linear regression, and then I've covered a code that I got from Kaggle where you can compute simple linear regression, and which is interesting because this was supposed to be an interview question, and it was saying use simple linear regression in an interview question, but I couldn't get simple linear regression to work on it. I only could get linear regression, but I might try to experiment some more and see for myself if I can get it to work. So thank you to my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you want to be notified whenever I make a new video, please press onto the tap of the bell button next to the subscribe button. And thank you again for watching my video. I look forward to making more videos for you in the future.